Good evening, everyone. On behalf of the Robotics Club of SNUC, I am delighted to welcome you all to today's expert session. Control systems are the foundation behind smooth robotic motion, stable drones, and intelligent autonomous systems. They transform mathematical models into precise real world actions and form a core pillar of modern robotics. We are honored to have with us Mr. Raghav Nallaperumal, an alumnus of Shiv Nadar University, Chennai, and robotics engineering graduate from Worcester Polytechnic Institute. With strong hands on expertise in robot control and dynamics, he brings both academic depth and real world engineering perspective to this session. Today, he will walk us through control system modeling, analysis, and design, connecting theory directly to practical applications. Without further delay, I invite Mr. Raghav Nallaperumal to take the session forward. Thank you.
Thank you, Sibin, for the introduction and welcome all to this session on controls and introduction to control systems. Quickly, let me just share my screen, and I hope my screen is visible. Yeah.
Yes.
So, so in today's session, we'll be talking briefly about control systems and how important is control systems from a robotics perspective. And the funny part is that we already know controls, we just don't know that we're using controls in our everyday life. So before we jump into controls and how the math behind it or how we're going to use controls in robotics, etc., let me give a brief introduction about myself. And yeah, so I am. Is my slide? One second. Yeah. So I am Raghav Nallaperumal. I'm currently doing my master's in robotics engineering at Worcester Polytechnic Institute, WPI. And in this last semester, well, the last semester was my first semester here, and I had the opportunity to work hands-on on a few robots, which I've shown in the slide here. The first one is called an open manipulator X. It's a small 4-degree freedom robot, which is a robotic arm. The one in the middle is called a crazy fly. It's a drone. It's a very small, it's almost just this size of my palm. So it's a very, very small drone with one of our favorite microcontrollers on it, which is ESP32. And of course, the last one being the Franca Panda, which is an industry level 6-degree freedom robotic arm. And I got the wonderful opportunity to work on all of these robots as part of my coursework and my research work here in WPA. And here's the link to my Medium article that about these robots, and I've written about my experience on working with these robots and an in-depth analysis of what all I've done and the projects I've done on these robots. So let's jump into controls now. And so, what exactly is controls? That's the big question that and this slide changed. Just a second. Yeah. So, what exactly is control? So, before we go too technically into what is controls or the math behind controls, let's start with a simple shower problem. So the shower problem is you want an ideal temperature for your water so that you have a good bath. So what is the action that you do? You turn your handle either left or right. You turn up the heat or you make it cold. So these are the two actions that you do in your shower. And what is the feedback? If it's too hot, you turn it back. If it's too cold, you turn it more. This exactly is what is a control system. And we've been using our shower every single day in our lives. And yet we didn't know that the shower is a control system or a control problem. So this is a very, very, very simple layman's example of what have the perfect temperature for your water in your shower. So this, in simple terms, is exactly what a control system's job is to perfect your goal. So let's move on to a more formal definition. Now that you've understood the concept behind what control is, and I've given you a very, very simple layman's example of what a control system is, let's jump to a more formal and a more robotics definition of a control system. A control system is a set of devices that manages, commands, directs, or regulates the behavior of other devices on our system. So, like we said, like in the in the shower example, the sensing was us, our skin. The water would fall on our skin, and we can feel if the water is too hot or if it's too cold, and then our brain would do the thinking of whether the water feels hot or cold, and then we would act on the shower and turn it back to adjust the temperature. So from a robotics perspective, if we look at it, we have sensors which sense information from the surroundings, and we have our main control system that does the thinking of what we need to do with that sensor input, and accordingly we have an output on acting out on our motors doing the same job. So this is a more formal definition of what a control system is, and how we use a control system in our robotics setup. So any questions till now? I'll pause for a few seconds, and if no questions, I'll proceed to the next. Okay, so I'm assuming there's no questions. Let's move on to the next topic, which is what is so control system can be of two types. It's called open loop control system and a closed loop control system. So, what exactly is an open loop control system and what exactly is a closed loop control system? So let's start first with a simple and easy to understand open loop control system, where the main difference being that there is no feedback. So, for example, our washing machines, our toasters, or any electric appliance that we use, for example, our we use dishwashers here, and so these electrical appliances, they do not have feedback. So, for example, if you run your washing machine, and if you say you set it to a certain setting and then it runs for 40 minutes, 50 minutes, it doesn't depend on whether the clothes are dry or whether the clothes are completely washed or not. It just runs for that particular amount of time and then it stops irrespective of the result. So is it really helpful to have an open loop control system? The answer is yes. For simpler devices and for simplicity, open loop control system is very helpful. So here, as you can see, action, let's say run for 30 seconds. There's no feedback. It will just run for 30 seconds and then it will stop. So that's how simple it is. And what are some advantages of this? Is that it's very simple to implement and it's very cheap since there is no feedback system involved, and it's just a simple input command and an output command which is happening in this case. So, and a simple analogy, if you want to understand what it's like walking with your eyes closed and hoping that you don't hit a wall. That's how an open loop control system works. And the major disadvantage of open loop control system is that if anything goes wrong, the entire system fails. And it's very difficult to identify which part of the system is causing what error. So your debugging for an open loop control system becomes very, very difficult. It could have been possible that it's a power failure, or it could be possible that there's an mistake in the circuit, or something in the circuit is not working. And it will be very difficult to identify that, since there is no feedback involved in an open loop control system. Let's jump now to a closed loop control system, which is what we majorly use in robotics. And what is the major difference? The major difference is that a closed loop control system has feedback. That is the major difference between an open loop and a closed loop control system. In a closed loop control system, your sensors, for example, your cruise system that you have in your cars, where you accelerate till a certain speed, and then the car just maintains that speed. So that, for example, is an example of a closed loop control system, where your sensors give feedback to the system, and your car is able to keep up the speed, and so it just continues to move at 60 kilometer per hour or miles per hour. And your and thermostat, for example, is another example of a closed loop control system, where it takes sensor input as the temperature in your house or in your surroundings, and it tries to balance the temperature and tries to reach that target temperature by assessing the temperature around us using the sensors. And like you can see here, yep, some of your pros are that it's more accurate, it's more robust, but the disadvantage being that since there's a feedback mechanism involved in this, it's more complex and more expensive. And another simple analogy here is that it's like walking with your eyes open. You see the wall and you stop. So that's a very simple analogy between open loop control systems and closed loop control systems. Again, I'll pause a few seconds in case you have any doubts. If not, I'll proceed to the next slide. And I'm assuming there's no doubts. You can put it in the chat as well if you don't want to unmute and speak, or if you feel like unmuting and talking, that also is fine. Okay, so let's just move to the next slide. And so here is a very simple circuit example, or a diagram of how open and closed loop control systems differ, where you can clearly see that the open loop is just an input. You're actuating, you give a reference input, your controller does some calculations, it gives an actuating input to your motors or your whatever your actuators are there, and then you get a controlled output. Meanwhile, in a closed loop, you see it's the same as an open loop, but the major difference being that here you have your a feedback mechanism, where once you get an output, you give the feedback to the input, and then your input value again changes based on the feedback that is given from your calculated output. So that's a major difference between the open and closed loop control. And this is a diagrammatic representation of both of these systems. So now let's jump to the next important concept of PD control, which I'm pretty sure everyone here has been waiting for to understand what exactly is PD control. And before we jump into the mathematics of what it is and the equations, etc., let's again let's go to a real life example that we see. Let's take an automatic car, for example. You have your accelerator and you have your brake. So what is a PD controller is that it has two main terms. That is, one is called the proportional term, or the P, and the other is called the derivative term, or the D. So what the P does is it's responsible for accelerating your system. So in a car, in the car analogy, it's almost as similar as your accelerator. And here I've written that it's very similar to a spring mass damper system that you've studied in physics. So if you remember your 11th and 12th standard physics, you would have come across a system called a spring damper system, where there's a block connected to a spring and then it has a damping along with it. So here in that spring damper system, your spring is an example of the proportional term, which helps you drive the movement of the mass block. And in case of a car, it's of course your accelerator. And the derivative term being your damping or your brake. So if you want your car to run in an ideal way, you will be using both your accelerator and your brake. You can't drive your car in an ideal speed or in an ideal way by just using an accelerator or by just using the brake. So hence we have a mix of both the accelerator and the brake in this. So that's what exactly my PD controller is going to do in any system that we're going to implement it in. So the goal here is the where am I and where do I want to be. So what my desired position is and where am I currently and how can I reach that position. So the error that we usually calculate is desired position minus current position, and the goal here is to use the PD control and to make it zero. That is the main goal here. So once again, a small recap is that the proportional term acts like an accelerator in your car, and your derivative term acts like a brake in your car. And for your system to work perfectly, as in to reach your desired states and your desired position, you will need both your accelerator and your brake to reach to that certain state and certain position. So that's why we'll be using something called the PD control. Of course, you would have also heard of something called a PID control, which is a slightly more improvised version of the PD control. But for this webinar, we'll be sticking to something called the PD control that we are learning here. So I hope the topic is clear as in why we are using PD control. And if there are no questions, we can move to the next slide. Okay, now a little bit of mathematics on how this PD controller works and what is this KP, what is KD, and you see a bunch of stuff on the screen, and I'll explain it one by one, as in how we are going to use these equations. But before we come to uh, 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 and a detailed explanation of these equations, I'll show you a few examples and then we can come back to a more detailed explanation on this equation. So for now, let's go through this a simple equation, which is ut is your control output. That is, for example, in your drone, it could be your motor torque or it could be your motor thrust. So it's your control output. And here we are multiplying a term called Kp, which is your proportional gain, and stiffness, which we explained in the previous slide. We multiply it by the position error, which is denoted by Et, where your error is a function of time, and then we add it with kd, which is again multiplied with the velocity error, which is a derivative of the e of t. So let's not jump into this complicated math for now. Let's go to some examples before we understand what exactly this PD control does. So let's go for the first example here, that I used PD control as a part of. So this was a controls final project that we had, where we had to implement a PD controller to make the drone follow a given trajectory. So this is the crazy fly drone that I had shown to you earlier. And the task given to us was to design a PD controller to make the drone follow the given trajectories. So, what exact trajectories did they give us to implement? These are the two trajectories that we have. So, as you can see, here are the 3D plots of how did our professor want us to make the drones move. And as you can see, it's a slightly complex trajectories, both of them. So the first one is a circular trajectory where the robot starts from a certain point, goes up, stops at that certain point, and then it has to move in a circular way, come back to that spot, and then again move and follow back and return to the position, starting position. The second one, however, is a slightly more super complicated path where the robot had to move in a diamond trajectory, not just up and down, but it had to move forward, backward as well. So it had a constant x direction velocity, so it was constantly moving forward as well. But at the same time, when you look at it from a YZ perspective, it should make a diamond shape as shown in the graph below. So these were the two trajectories that we had to make the drone follow. And yes, these are some of the equations and how the project was set up, so that we had to write. So these are some complicated jargons for now, which we will avoid. But a trajectory planner is basically something which helps us generate our desired trajectory. So the graph that you saw in the previous slide was the output of that trajectory planner. So that so let's we won't be going into the details of that, but we will stick to our control part, where here we had two control systems. One is a position controller, and two is second is an attitude controller. So what exactly is an attitude control? So if you look at a drone, there are two things that you need to look for in the drone. So one being its movement in the 3D plane, that is forward, backward, X, Y, up and down, etc. And the second, it's its orientation. How do you want the drone to be oriented? So what your outer loop, that is your position control, does is that it is helping us control the movement of the drone in X, Y, Z plane and in the 3D space as it is. And what your attitude control does is it will adjust your torques of the motors on your drones, so that you can orient your drone as and however you want it to be, and whatever your desired drone position or orientation is. So it could be straight, it could be slightly tilted. So one of the other projects as part of our control systems, where one of my friends, he worked on something where he tried to flip a drone and tried to maintain that orientation or continue that trajectory. So he tried to do this kind of a trajectory where he flipped the drone, and it drone still didn't fall to the ground. So you can literally do anything with your controllers. And like Sibin mentioned in our introduction, that using control systems, you can control your motion and trajectory of your drones. So this is a very simple uh, outer overview. We will again, the math is a little complex for the scope of this webinar, but it's a very outline view on how exactly the drone control systems work. So you have a position control, and you have an attitude control, and you have your motor controllers, and your, of course, your rigid body dynamics of your drone as part of this. So these are the few. equations. And yeah, so let's do a small simulation demo of what I talked about, where I wanted to make the drone move in a circular trajectory as shown in one of the previous slides. And until I set up the simulation, if we have any doubts, let's put them in the chat, or if you have any questions or suggestions.
Yeah.
If you have any suggestions, do let me know. But give me a few seconds to just run the simulation, to set up the simulation, and then we will move ahead in the presentation. Any questions? Okay, so let's go ahead to our simulation here, and let me quickly share my screen again. Yes, I hope my screen is visible. And so this is what I'll be running the simulation. And before I continue, I'll give credits to my controls professor, and because they gave us a very baseline template on of this, and then we just had to build our controls on top of it and write the equations. So credits to my controls professor. And before we jump into the simulation, I'll show you a small snippet of the code where we write the controls of the system. And here you can see I have a KP value, I have a KD value here. As I showed you in the presentation, we have KP and KD in our equations. And here you can see a clear indication of how we are implementing um, PD control into the drone. Of course, we have a few more additional terms in this because the equations for a drone are slightly more advanced than the equation I showed you in the presentation. But the key aspect here being is that Kp into the position errors and then Kd into the velocity errors. So I am implementing exactly what we talked about in the presentation here, and of course a few more adjustments which come with the project. So this is what I wanted to show you, and as in how simple, how easy it is to implement your PD control. I'm just calculating my position error here using the target pulse and the current position, and I'm calculating my velocity error here with target velocity and my current velocity, and I'm computing my desired thrust by just multiplying Kp with my error position and Kd with my error velocity. So it's as simple as just my as the equation that we saw in the presentation, and implementing it is also just a few lines of simple code which is not too complex. So let me quickly run the simulation for you, and I hope it's visible. As you can see here, you can see the drone moving, and I'm not sure if you can see the drone moving in the video, but if you want, I can run it again. Can someone just confirm if you were able to see the drone move in the presentation?
It's actually moving very slowly. Yeah,
Yeah,
yes,
yeah, I
yes,
think it's getting stuck. I'll try to run it again, but if not, I'll just add a. Okay, I think now it should be more clearly visible.
yeah, it's visible now. Yeah.
Yeah, yeah, yeah. So I'll run it once again, and try and observe how the drone is moving, and Okay, so it's starting from a start point and then it's moving up to a certain fixed point, and then it's moving in the circular trajectory and coming back to that point, and then it's slowly moving back to the same point that it was supposed to come back to. So these are a few graphs showing the tracking of the drone. And here, if you look at my terminal, you can see the tracking performance of the drone and you see how small the errors are. It's almost in millimeters, 0.0004. So that's how accurate the tuning has been in the simulation. So, and now if I can, if I come back to my presentation quickly, in just a second. Why, how, what is the difficult part in this is figuring out the KP and KD values, because that's what is called tuning a controller. So the desired motion that we saw in the simulation is something which is achieved through tuning this KP value and KD value. And let's go back again to the accelerator and brake example, because when you have your drone moving in that particular trajectory, so first it's stopping here, and then it's accelerating to a certain point, and then it's again braking so that it stops when it reaches the destination point, and then again it is accelerating in the circle, and then it's decelerating so that it slows down by the time it reaches the end goal. Then it is again accelerating till somewhere in the middle, and then again it is decelerating to so that it reaches to the start point with and stops there. So it's a work of both the accelerator and the brake, accelerator brake, accelerator brake. So when we do that, it is important that our KP and KD values are tuned to the perfect values. And trust me, tuning KPKD values is not light work. It's a lot of you require patience, and it requires you to understand what is causing which error, and by changing KP value, what it's going to do to the system, and by changing KD value, what it is going to do to the system. It's important that you sit and experiment with your KP and KD values and ultimately reach the final value which works for the system and gives you minimal errors. So now that we saw a simulation demo, I would proudly like to show you a video of my simulation. So the simulation was a part of the project, and the final project was the real life demo of the robot. And I was surprisingly, I was able to do pretty well in the demo, and I the error was pretty less compared to what I expected it to be. So I will show you a small video of the yeah, I think it should be up now. And just a second. Yeah. So this is a small video of how the drone was moving in real life. And as you can see, it's following the perfect circle trajectory and coming and stopping where it should, and then coming and stopping again at the start point. So I'll play the video once again, just in case. So it's going up, start going to the start point of the circle. It's moving in the circular trajectory as it should, and then it's coming down to the start point and stopping. So that was how, isn't it exactly similar to how it was in the simulation? You saw the movement of the drone in the simulation. It moved up, moved in a circular trajectory, and then it moved down to, and then it moved down and stopped to the starting point. And if you look at it in the demo video as well, you see somewhat of a similar motion. But here's where I will come to something important in not just controls but in robotics in general is your sim to real difference, where your results in simulation and your results in your real life robots vary a lot. So if you look at some of the plots here, let's focus on the right side plot for now. So if you see there's a blue trajectory, right? So your blue dotted line trajectory is your desired trajectory of how the robot should be actually moving, and your red line is how the robot actually moves in real life. So as you can see here, the robot is moving in a circle, but you can see that it's not exactly overlapping the desired trajectory, and it has a few errors. And if you look at this Z part especially, there is a few the error can be slightly larger compared to other terms in X and Y. So sim to real is a huge concept and a huge part of robotics, where everything which works in simulation and everything which works in your computer need not necessarily work in your real life robot, because in your simulation you assume a few things which for example, you assume there is no friction, you assume there is no drag, because when your robot is moving in the air and its rotors are moving, obviously it is going to create some disturbance in the air, and that is going to affect your movement of the robot. So considering those aspects in simulation is very difficult, but some of the simulators do a real good job in trying to simulate real life environments. One of them being Isaac Sim, which is one of the good simulators. But even in Isaac Sim and your real life robots, obviously there is going to be a lot of difference. So you can clearly see how the difference between the errors in your simulation and your errors in your real life testing of the drone. And after that, this was one of the projects which I did as part of this semester. And the second one, I'll show you another example of where you can implement PD control is in your robotic arm. And I showed you the open manipulatrix at the beginning of the presentation in my introductory slide. Yeah, the one here. So this is an open manipulator X. It's a robotic arm. And again, we implemented PD control as part of our project for using the open manipulator X as well. So let me come to my slide on the open manipulator X. So as you can see, the task was to move the robot along positive y-axis. So my robot is set up now. And if you see, and if you would have noticed a jerk at that, um, let me just quickly show it again. So if you notice, there's a jerk when I press enter, and what happens is that why is that jerk? Is that my controller starts running, so that's why there's a sudden jerk in the robot. And then now I give my command to make the end effector move along the y-axis. So as you can see, the robot is slowly moving towards y-axis. Let me run that for you again so that you can see the demonstration. So it stops, and then gives a sudden jerk, right? And then that's when the controller is running, and then you give the velocity command, and then it just moves along positive y-axis. So if you can see, this is the graph of the end effector trajectory, and you can see that it's not a complete proper straight line. It's almost a straight line, and this is what we achieved through using a PD controller. We wanted the y velocity to be a straight line, and we were able to achieve that. Here, this is a position, this is the time. So as you know from your 11th and 12th standard physics, that position, the slope of your position time graph is your velocity, and here the slope is nearly constant throughout towards the entire duration of the motion. And that's what we were able to achieve by using a PD controller in the open manipulatrix. And something I talked about in the previous slides is the simulation versus real life errors. And if you look at my graph for the simulations, you see here that there is nearly any error which is not visible to our eyes. So you can see the green and the red lines almost overlapping in these cases. But these plots are from the real life experiment, the video that I showed you where the drone was running in the real life, and you can clearly see the amount of error that is there in your real life experiments. You see a lot of vibrations, you see a lot of disturbances, a lot of noise in your drones plotting. And here, as you can see the example, in the simulation, you have nearly perfect physics, and you have almost infinite battery. So your accuracy is almost in millimeters, which is about 4.8 millimeters in my case for the drone. But if you do the same in real life, and if you run the same code, the same PD values, the same setup, you have additional problems. That is air resistance, you have battery, you have delay in communication because you send your commands from your laptop to the drone. Like I mentioned previously, we were using an ESP32 on the drone. So you send commands from your laptop to the drone. So there's communication delays, because of which your error is almost in centimeters. It moves from 4.8 millimeters in error to about 8 centimeters in error. So which is almost 20 times more. Um, so this was the few points that I wanted to discuss in today's webinar, and we introduced a quick recap on what we did this in this webinar. Is we looked at what is the basics of control, and we looked at a formal definition of what is control. We looked at what is open loop and closed loop control, and how the advantages, disadvantages, and where exactly each of these types of control systems are used. Then we looked at the architecture diagram, and then we looked at the PD control, what exactly it is and how it is used. Then we looked at the mathematical equation, and then we came to the project demonstrations of how we implemented PD control in the drone, and how we implemented PD control in the open manipulator X as well. And then we talked about the final point being simulation versus real life. How different is simulation versus real life? So, any questions you have? I will pause for a few more moments. And okay, before questions, I would quickly like to give a few credits. One is to my robots control professor, which is who's called Gondre Lee. Do follow him on LinkedIn, and if you did like this webinar, do tell him that I conducted this seminar and that you liked the introduction to controls, and of course our very own robotics club for inviting me to give this lecture on controls and a very brief introduction to controls and a few ideas on how to implement these basic controls in your upcoming robotics projects. So before I wrap up, I will open the floor for a few questions. And if you have any questions, you can put them in the chat, or you can also unmute and talk to me as well. And I'll pause for a few seconds. Okay, okay, sorry, my bad. And just guide me on what I should do to enter control systems domain and tell me what are the resources. Um, um, okay, so a few resources. Okay, let me just search up that resource quickly, because before you go into robotics control, it is important that you understand the fundamentals of what control is. And just give me a second. There's a YouTube channel with um, uh, amazing resource for control systems. So I will, yeah, I will share my screen. And here, okay, so I hope you can see my screen. There's this channel called Brian Douglas. So before my first semester here, even I was not, I didn't know much about controls. So this was the channel that I referred to, and and the lectures and explanation are very easy to understand. So I would suggest you start off with understanding basic control systems. And about how can you gain skills, any project you use where there is a sensor input, there is a action performed, and then there is a actuator output, like your even your basic IoT projects, you can use your PD controller to get um, good results. So in terms of implementing controls, literally any project which has an input, a thinking part, and then an output, you can use controls in those projects. And as far as resources is concerned, I think this would be a very good place to start your controls with. Okay, so there's a question on, I'm doing a self-balancing bot and I'm stuck in finding the exact KP and KD values for balance. Could you suggest what to do? So, see, this is when implementing PD control, this is one of the biggest problems that everyone faces. That is identifying the right value of KP and KD. So, there is no hard and fast rule on how that you should implement PD control. Like you should try and tune it in a certain way. But I would suggest you to start with extreme conditions. Like for example, you start, let's say, for example, let's start at a middle value. For example, let's say I'm using zero point 0.5 for my my KP and KD, and keep your D value constant first and try to push your KP values, try to keep increasing your KP values, and see what is like a boundary condition. your maximum limit to which you can push your KP, and or keep your KP value constant and try pushing your maximum KD values, and you'll find like boundary conditions for both KP and KD, and then you keep tuning these values to get an ideal value. There is no hard and fast rule on uh, how you should tune your KPKD values, but I would say that is a good place to start with. Is you start with a certain value, you keep one of the values constant, try changing, increasing, decreasing your KP value, and then keep your KP value constant and try changing your KD values by increasing it, decreasing it. So that would be my suggestion. Also, please don't call me sir. You can just call me Raghav. And is there any way to simulate it? We are finding it difficult to update KP each time, load the code in Arduino, and run and see. For that, I'm not sure if you can simulate it to test it, but um, if you find any self-balancing bot simulations in your, then maybe yes. But obviously, like I explained, your simulation to real robot difference will vary a lot. So even if you do it in simulation, when you run it on your real robot, you will have to again rerun it and retune it again so that it works for your real life robot as well. So I would still suggest that you do it directly on your real life robot, because it's it won't be a pain to tune it again, because if you do it in simulation, you'll have to first tune it in simulation, make it work in simulation, and then when you load it onto your robot, there'll be sorry, there'll be errors, of course. So you'll have to retune it again and make it work on your robot. So I know it sounds very painful and it sounds very time consuming, but that's the way to do it, unfortunately. Any more questions or any more suggestions on the webinar? Is it like based on the degree of freedom of our system, the number of control loop functions decided? No, that's not necessary. So it's not based on a degree of freedom as such. It's based on what you want to make the robot to do. So, for example, even in the drone system, I can make it work just like if I don't want my robot, my drone to tilt at all, I could work without an attitude controller, but that is not suggested, of course. It's always advised to have an attitude controller so that your drone maintains its stability, but your number of loop functions is not exactly based on degree of freedom, but it's more so on the nature of the task that you want to perform. So for the example that I gave in the presentation, the drone, you had two tasks which you had to do. One, you had to make the drone move forward and backward. Second, you had to make the drone move, like rotate it and maintain a certain orientation. So when you do that, you require two loops. I could say the same for my robotic arm as well. In my arm, I used just position control because for me it didn't matter how my end effector was present. It just mattered that it's moving in a plus y velocity. But let's say I had I my task was to grip it in a certain position or rotate my end effector as well. In that case, I would have to use an attitude controller to manage my orientation of the gripper. So it's not really based on your um, degree of freedom as such, more so to do with what your task for that particular robot is. If it's just a movement and your orientation really doesn't matter, then you can simply work with just a position control. But if your orientation also matters, then you have to include an attitude control into that control loop. So hope that makes sense. And where I talked about in depth, I discussed how I worked on each of these projects and what exactly was the task in each of these projects and how do they work. So I would suggest you go to the link and give it a read. And if you have any more questions, you can always reach out to me on LinkedIn, or I can also give my email, and you can always reach out to me, not just regarding the webinar, but any doubts regarding robotics in general as well. So, yeah, I think we can wrap it up with that.
Thank you, Raghavana, for this interesting session. We learned really a lot. Even though the control system concepts are very complex, you told us in very simple layman terms, and it was very interesting throughout this hour.
Thank you. Thank you. I'll drop my contact details if you guys want in the uh, chat. And yes, of course, you can. I'll hand it over to Sibin.
Thank you guys for attending it. Hope you learned a lot today. So do follow us on our Instagram page and scan this QR to join our WhatsApp group. And don't forget to give your feedbacks, and you can get your certificate by scanning this QR code. Other college students, if you don't find your course in the feedback form, just select a random. It shouldn't be a problem. And once again, thank you all for attending today's webinar. Thank you.